Quantum Mechanics Lesson 8, Conservation Laws. We've been talking about a lot of different things that need to be conserved during quantum decays. Today we're going to be looking at them and using a couple of examples to check, and then you're going to have to start doing a bunch of examples yourself. So, first of all, what are the things that need to be conserved whenever something decays? Well, they are charge. Remember, charge is a property of some matter. Up and down quarks have charge. Some of the leptons also have charge. Then there is lepton number. Remember, that needs to be conserved separately for electrons and muons. So you need to track the electron lepton number and the muon lepton number. Then we have mass energy. Remember, that needs to be conserved, but not mass nor energy needs to be conserved, but the combination of them linked through the equation E equals mc squared. Finally, baryon number needs to be conserved. So, let's see how this all plays out. The way it will normally work in your exam is they will give you a proposed particle decay and then ask, could this happen? And you need to run through each of these conservation laws and check. So, let us imagine that a neutron decays into a proton and an electron and an anti-electron neutrino. Remember, the line above something indicates it is an anti-version of that. The way I would literally do this in the exam to make it really explicit what's going on is I would go through each of them one by one to show your working. So let's start with charge. The charge of a neutron is 0, and that is going to the charge of a proton, which is 1, charge of an electron, which is -1, plus an anti-electron neutrino. Neutrinos have no charge, so that's 0. So that equals 0, so that's okay. We've got 0 before and 0 afterwards. Next, we've got lepton number. Now, there's no muons here, so we just need to check the electron lepton number. Before, again, we've got 0. Neutron doesn't have an electron lepton number, and that's going to 0 plus 1 for our electron, -1 because it's an anti-electron neutrino. That equals 0, so we're okay on that. Mass energy, if they haven't given you numbers, you don't know. But one thing to always remember is things can't decay into something bigger than them. That just can't happen. So if you've got something with 2 quarks decaying into something with 3 quarks, well, that'd be weird, right? We've just gained mass from somewhere. We can gain mass, but only if we put loads of energy in. That's not really decaying, that's something else. That's mass turning into energy, like in a cosmic ray or inside the Large Hadron Collider. So you only need to worry about this if they give you the numbers. Similarly, momentum must also be conserved, but again, unless they're telling you something about the angles things are moving at, you probably don't need to worry about that. Finally, we have baryon number. The baryon number of a neutron is 1. That's turning into baryon number of a proton is 1. Add 0 for our electrons. It has no quarks, therefore no baryon number. Add 0 for our neutrino, so 1, 1, and that all works. 1 before, 1 afterwards. So we can see that this decay could, in fact, happen. Let's take a slightly more complicated decay. Let us imagine that a negative pion, a pion is a meson with 2 quarks, a quark and an antiquark pair, like all mesons. It is made of an anti-up quark and a down quark, thus giving it its charge of -1. That's going to decay into a negative muon, so that's a muon with a minus charge, and a muon neutrino. neutrino. Let's go through. So, charge, well, we've got -1 before. That's changing into -1 plus 0. So that's all right. Lepton number, well, we've got 0 before. So that's all right. But then our muon, my negative muon has a muon lepton number of 1 plus, this is a normal muon neutrino. So that's got a muon lepton number of 1, so that equals 2. So this could not happen. We don't even need to look at the rest of them now. Once one of the conservation laws has been broken, we know it cannot happen. If we were to try and solve this, we would have to make this an anti-muon neutrino. Thus, the muon lepton number of this would be -1, and then it would all work out. If we were just to quickly check baryon number, this of course has a baryon number of 0 because it's a quark and an antiquark. So -1/3 plus 1/3, 0. This is 0 because muon, remember, is a lepton. So overall baryon number would be conserved. So if it were not for this being a normal muon neutrino and not an anti-muon neutrino, everything would be fine. So this is how to do this sort of question. Write out charge, electron lepton number if you need it, muon lepton number if you need it, baryon number, check they all conserve, and then you will have your answer. There's a bunch of these in your task for this week. Best of luck, off you go.